Hello everyone and welcome. In this episode I will connect an energy meter using an Arduino to my Magic Mirror so I can read the consumption of the heat pump. So the energy meter will specifically be monitoring just the heat pump. Welcome and hope you enjoy. There are many alternatives to setting an energy meter on the heat pump. I looked at some other alternatives as well, but I finally ended up with putting in a real energy meter, so to say, mostly because of the accuracy of them, and I knew that I could rely on them. And there are a couple of different types out there. So in my case, I looked at 3 types. First, you can get the normal ones with a pulse interface, and that's basically a LED that is blinking in the ratio of the consumption. That's fairly limited, and it can only give you the current consumption, so it's a lot of work to analyze more data and measure the kilowatts per hour and things like that. So that was out of the question. And then you have some intelligent ones. There's a normal Modbus interface. And well, I thought about that, but then I read a bit about it, and from that information, it seems like the MBus is a more modern interface and a bit more flexible, and it's used specifically for energy metering applications. So I went with that one. It turned out to be a bit more work to interface with it, but in the end, it will do the job. So MBus it was. I tried to find one with Modbus TCP/IP, and if I could have that, I wouldn't need an extra Arduino to control it. But I couldn't find a good alternative there, so I decided to use the MBus and interface it with an Arduino. Here is my setup for the Energymeter that I'm going to use for the heat pump. It's an EM340 from Carlo Gavassi. This model has MBus interface. This model has an MBus interface, as you can see on 7 and 8 terminals. I believe I also have a model with Modbus if you want, or just a pulse LED interface if you want that. So I have set up the test here, and what I'm trying to do is that I'm trying to get it to run on a lower voltage, because now I need to use a 34 volt as the MBus interface is based on 34 volts. Here you can see the communication. Let me stop it for you. You can see in yellow the outgoing message from the Arduino and then the response below. And this works fine on 34 volts, but as I said, I tried to bring it down to maybe 12 volts, but I was not able to get it lower than 16 actually, and still be reliable. So I decided to use 24 volts instead, and that works fine. You can see I'm using the Arduino Nano and the extra serial port, and it's communicating directly with the Energymeter. So let's have a look at the schematic. As you saw in my testing, the MBus is actually a 34 volt interface. But I didn't want to have that, so I did some experiments, and I found out that using 24 volt I could get it reliable and good signals without any issues. So I went with the 24 volt, and I have an external power supply, a normal adapter, which gives out 24 volt DC, and it comes in here, and I have put in a DC-DC converter to drive the Arduino. I could almost drive the Arduino directly, since I think it's good for 17 volt or something. But I didn't want to risk that, so I put in a DC-DC converter and brought it down to 5 volt. And then I'm using the 24 volt for the M-bus interface. I don't know if it will work in every application, but it was reliable, at least with my. I think that the important thing is that you get the gap between the 0 and the 1, and that's what's interesting. So, and then if we look at the interface, we can see that we have the transmit signal coming out here, going into this transistor. And as long as this transmit signal is low, we will not drive this transistor. That means that we will not drive this PNP transistor, since the divider here will keep the base to a high level. So this will be open, and that means that the level here and here will be almost the same. And since we have 24 volt here, we will have that on the second terminal as well. So that means that the voltage gap will be 0 volt, and that means low signal transmitted on the M-bus. And if we drive it high instead, we're transmitting, then we will drive this transistor, and that means that we will drive the PNP transistor as well, since this will be low signal on the base. So this will be closed, and since this resistor is much lower than this one, we will have almost 24 volt gap between the terminals, and that will drive a high signal on the M-bus. So when we have a high signal out, that's actually when we can receive data as well. So the high signal will mean that we are not sending any signals out on the M-bus, and we are ready to receive information. So if we first check if we get a 24 volt gap on the M-bus, that means that this will be 24 volt, and this point here will almost be 0 volt. And that means that this point will also be 0, and we will not drive the transistor here, and the voltage divider here will decide signal into the receive. And the divider here is because of the 24 volt, taking it down to 5 volt. So that will be a nice high signal into the Arduino. On the other hand, if we get 0 volt on the M-bus, that means that we will have 24 volt here, and that will actually rise the signal level on the base of the transistor and driving this transistor, and that would pull down our signal into the Arduino, making a low level on the receive. So that's the way we can receive on the M-bus as well. These values on the resistors here are kind of critical. So if you change the levels of your, if you change it from 24 volt to something else, then you maybe need to adjust these resistors and test it so it still works. So I have mounted the Arduino and the DC-DC converter and the interface circuits on a board. I printed a 3D casing, so I'm test mounting it now. So we need to have a look at the specification before coding this. And you can find different documents out on the internet, and one is the M-bus specification, and this will give you all the details of the M-bus and how it works and so on. I will include the links in the description, and then I have a PDF that is more specific for this Energymeter and has a bit more details on what's exactly we want to use for this Energymeter. And I have tried to summarize this in a slide that I will show you here. You can communicate with the Energymeter in different ways. But since I just want to keep receiving information about the status and the values, I selected to use the FCB-FCV protocol. And what this means is that you have a control bit in the control byte that is called FCB. So if I send a control value with the FCB bit set, the Energymeter will return the FCB bit 0 in the response. And then I'm supposed to check that and see that everything is okay, and then I will send it back with an FCB bit of 0, and then the Energymeter will return an FCB bit of 1. And the reason for this is that if I find anything wrong in the response that I get, it could be a checksum error or something else, then I can just retransmit with the same FCB bit as I did last time, and the Energymeter will repeat the frame that I have missed. So to simplify this, you just need to toggle sending 7B, 7, and 5B to the Energymeter. And if you switch that every time you're sending, the Energymeter will keep sending frames one by one, depending on, could be 4, 5, 6 frames. It doesn't really matter because it will just go around and it will just send the next frame in line. And that means that I will receive continuous data from the Energymeter. So this is a really simple way of controlling the data flow. This is the response that we will get back. And here is some information about the Energymeter, versions, and manufacturer, and so on. But I will only use 2 pieces of information here. The second byte I will determines the size of the complete message. So I will use that to make sure that I receive all the bytes in the frame, because it can vary quite a bit in size, each frame. And the second part is actually what contains the control codes, the information about the unit of measure, and it contains, of course, the data and the values. And this part I will show you how to handle. And then I can also check the checksum. I'm not doing that in my example. I'm just checking the MDH byte that I receive, which is the termination byte, and it's should be 1F. And if I receive that, I determine that, okay, the message was probably okay. So if we look at the different frames that we can get from the Energymeter, this is specific for my Energymeter, but I believe it's similar to other Energymeters and kind of a standard. And you can see that I will actually receive 5 different frames. I will not really care about which frame I receive. I will just extract the values from the information I get and then read whatever necessary, but I will still go through all the frames and then loop back to the first frame and receive new values for that one. This will typically take some 10 seconds or something to go through all of the frames. And if we have a look at the data part of the message and the control parts. This can be a bit tricky to analyze because, as you see in the first picture, we can have a different length of the control codes. We can have different unit of measure, and we can also have different data format or lengths of the actual value. So if you want to analyze this completely, it's quite a lot of work. So what I decided to do is that I will read the first values and try to find a fingerprint. So I will just compare it to a list of the values that I want to receive, which are unique. So in my example here, if I receive 4 and then 5 in the second byte, that will be enough to determine a fingerprint that, okay, I know that I have received the consumed kilowatt hours from the Energymeter. And then I will also have another list of values, a static list that will let me know that, okay, then I know that the value I have received needs to be multiplied by 100, and then I will get it in watt hours. And in that way, I don't need to analyze every single byte here to understand how to interpret everything. So it's kind of a static list, but it will in any case be the same every time. And if you can look a bit down in the table here, you can see that some of the measurements have quite a lot of different bytes and varying length and so. So it's quite hard to do that. And in this way, it's much simpler. So now we're ready to start coding. I have opened up my project in Visual Studio Code, and I will make the Arduino program first. And to start with, I have created the fingerprints that I've been talking about. I have basically added the values from the documentation that I want to check, to monitor the values of. And as you can see, it ended up being 8 bytes to identify a unique fingerprint. And actually it will work in this way that I will just read until I find the integral 0. So the first 2 characters only need to match here in this example, 4 and 5. And then I will stop reading. And in the next case, I will just make sure that these match. And then I have checked that this will be a unique fingerprint of the data. So this is the first list here. And then I have another list, and the index is the same. So the first line is the fingerprint of the first line here in this array. And here I've selected to enter the frame number, even if I'm not using it, the clear text of the measured value, the unit of measure, and also the multiplying factor. So in this case, I will be multiplying everything with 100 to get kilowatt hours to present. So these 2 arrays I will use. And for easy demonstration, I've created a test message here. So this is an actual message that I received from the Energymeter, the first frame, and all the values. I will be using that to simplify the testing and debugging of especially of decoding the message structure. So let's have a look at the main program. First I have a setup, setting up the baud rate. This is for the serial debug. And then 9600 baud rate for the communication with the Energymeter. And as you can see, it's also set up to even parity and one stop bit. I'm initializing the Wi-Fi. I will come back to that. And that's because I will upload this to the Magic Mirror, naturally. And then if we move down to the main, I'm also checking the Wi-Fi here to see the status. And if I have lost connection, I will reconnect every 20 seconds to make sure that. We can skip this part here for now. This is just loading the test message instead of the receiving any data. But if we would be connected for real, what I would do is first I would request new data every 3 seconds. And we will have a look at this function, request data. And then I would check the serial port to see if there are any data available as a response. And if there is any, I will execute the receive data function and retrieve the message and decode the message. And the last piece here is for uploading the data to the Magic Mirror. So we will have a look at that function as well. And I'm typically uploading the data every 20 seconds here. So quite frequently updated, and then just at the end printing some data on the console as well for easy debugging. So looking at the request data function first of all. And as I explained earlier, we only need to do 2 things. We will send the control byte of 7B and then alternate with sending 5B. And if we continue doing this, we will receive back the 1 frame at a time, and it's counting up the frames and sending me 1 by 1. So it will continuously update my data every time I send these codes. So it's really simple setup here, and I'm having a variable to keep track of what I did the last time, and then I just sending the different FCB bits here. So I'm calling for the function send short message. So let's go and have a look at that. It's also really simple. I'm only sending according to the structure of the message to the protocol that we looked at before. We first send the start byte. It's always 10 in hex. And then we're sending the command, and this would be either 7B or 5B. We're sending the address, which is always set to 1. Since I only have 1 meter, you could potentially have a lot of meters on your M-bus connection, so that would work fine. And then we're calculating the checksum on this one and sending the stop byte. So it's an easy protocol, and it's quite easy to start with these commands. And then at the end, I'm writing it to the serial port, and I'm telling the system it's 5 bytes. So that's simple enough. The next thing we want to do is have a look at receiving. Receiving data. So here we are checking to see that there are any data available. And if we have any data available in the buffer, we will start reading it. And I will first read the 4 first bytes. And the reason for this is that I want to get the size of the message. and I will put that into the variable message size. And then I will do some debug printing, and then I will check that the message size is reasonable. In this case, I've set it should be between 0 and 300, otherwise it's not reasonable. And when that's established, I can move down a bit here. I will receive the full message. And in this case, I will tell the system, read all the bytes, and I will put the message size plus 2 bytes. I think it's the checksum and the stop bit that is not included in the message size. And this is actually really important, because first I tried to receive data as soon as it was available in the buffer, but that didn't work out quite as I had hoped for. I was missing bytes, probably due to the timing and so, and the quick response I need to do when I'm reading byte for byte from the buffer, and also the buffer size could be limiting here. So what I found out was that the best thing is to read all of the message at once. So here I'm telling the system, read all the bytes, and then I will work with what I received. I'm checking the control character here, 1F, or the stop byte, or whatever it's called, and to make sure that I've received the whole frame. And if not, I will return a message, and I will stop doing anything more. The next thing we want to do is to decode a message. So here I will call for another function to decode the message that we have just received. And I've simplified this as well. As you know, I like to do it quite simple, and maybe for some it's not covering all the situations and so on, but I don't really want to spend time on building a library that will handle all situations and all types of messages and all types of energy meters and so on. I really just want to make the minimum to achieve what I want here. I could always evolve the program if needed, if I have other meters being hooked up and so on, but I'm trying to stay very simple here. And you can see that here as well. So I'm sending the pointer to the buffer and also the message size to decode this message. So what I will do is that I will start from the start of the data I'm interested in, or rather where I have decided to make the fingerprints from. And this is from byte 20. So I will start reading and comparing with my fingerprints to find out if I have a matching fingerprint. And if I find something, we'll move a bit down, I will set the flag found. So I will loop through all of the fingerprints in my array, and I will compare it to the data I just received. And if I find one of the fingerprints, I will go into this function, and it will really simply identify what position or what fingerprint in the array that I found, and then I will do different things for that. So for example, if I found the fingerprint with index of 7, I know it's the line voltage, and I will set the line voltage to the value of the data set that I received. So maybe not the most efficient way of doing this, but as I said, simple enough. And then I will continue down and I will move on to the next message, because there could be, as you saw in the specification, there could be 10 values in one frame, and I want to scan all of the values. So then I will do a new fingerprint check and see if I found any values. And doing it in this way, I will not really have to care about what frame it is and all of that. I can just find a match, and then I will update the value if I find it. So now we have decoded the message as well. And the next thing is that we want to send it to the Magic Mirror, or update the Magic Mirror with the new data. And this is, I will not spend so much time on this because it's actually the same function that I have used for all my similar projects with Arduino and Magic Mirror. And I'm calling it upload results. And the basis of it is that I establish a connection to my Magic Mirror on the Raspberry Pi. In this case, I'm using port 8082. And then I'm checking that I am connected. And if not, I will reconnect. And moving down here, I will construct a JSON document using this function. And I said that it will be a maximum of 1,000 characters in this JSON document. And then I start adding my items that I want to send to the Magic Mirror. Energy data, voltage, current, effect. And then I will also post it to my Flask web server page on the Raspberry. So this is important that we have this receiving end, and that is what we will have a look at next, how to receive this data into the Raspberry Pi and a Magic Mirror so we can use the data. And then we're closing checking the response from the Magic Mirror and closing and disconnecting. So if you have watched my other videos with Arduino and Magic Mirror, you probably recognize all of this code. Otherwise, you can go back and have a look where I discuss it in a bit more detail than in this video. So moving down to the main, I can test run it now because I will send a request for data, but I will probably never receive anything since I'm not connected to Energymeter. But instead, I will populate my message buffer with the test data that I have specified. So let's have go at that. Let's download it. And have a look at the code. Then you can see it's connected to the Wi-Fi and it's decoding the message here. And I'm receiving a new message, so to say, as a test message every 10 seconds here. And you can also see that I'm sending alternating between sending 7B and 5B. And now I get an upload error here because we haven't done the part in the Raspberry Pi yet. I don't know if you spotted, but it did actually upload. And I think I know why. Things happen. Yes, so when my demo Raspberry server didn't reply, it reconnected to my main Raspberry Pi. So it actually updated my real Raspberry Pi. I will change that. I don't want to corrupt my data on the production server. So open up my Python program in the Raspberry Pi for my Magic Mirror. And I'm using the demo project that I have had in previous videos and just adding on new functionality to that demo project. The first thing I want to do is to have somewhere to store my data. And since I already have my main energy meter, I'm using the same structure, the same class. We'll just add another class array here for my Energymeter 2. And then we need to receive the data. And as you saw in the Arduino, I will post the data to the page Energymeter 2. And here I will just add values I want into the array of Energymeter 2 and that class type. And then I will add some runtime data as well to store it. So very simple page to receive that data. Now we have the information in our Energymeter 2. We need to present it on the page. As you might remember, I have two main pages. And the first one is the index page where I store all variables for debugging and to check if there are any other data that I want to include. So I will be adding all of the Energymeter information to this index page, like this. And the next is the main page of the Magic Mirror. And here I have also constructed some extra values that I will show you later on what it's used for. And the point here is that since I now know how much energy goes to my heat pump, I can determine three things. I can determine how many kilowatt hours are I'm using for heating, how many are I using for hot water, and how many are I using for the rest of the house for normal energy consumption. And this can be really interesting to see how much of the energy is spent on different items. And this is what I will show with these bars here. And then I need to send this back to the web page as well. And I have some timers here as well, like this. So that's the main page. Looking at the log function, I will be adding actually three different values here. I will have the energy meter per hour consumption, but I have also established energy meter for heating and for water. So energy meter for heating and water, adding those together will be the total amount of kilowatts that the heat pump is drawing, and that will be stored in this one. So this is so I can be able to see the difference between heat, hot water, and the rest of it. So I'm storing those values and I'm recording them hour by hour, and I will also be storing it in the database based on the consumption per hour, in the same way as I do for the other energy meter. I've added it to the SQL statements here. So I'm storing and updating the data. And I will also add it here so that I reset it when the hour change. Then we need to create some statistics as well. And to start with, I'm creating two statistic values. And one is for the daily consumption and one is for the monthly consumption. So in this way, I can also see how much energy goes to heating and to water and to the rest on a monthly or daily basis. And since I have all the data by hour in the SQL Server database, it's no problem to add any other statistics or extracted statistics to Excel and do some more advanced things there. And if you haven't looked at my earlier video about that, you can go back and have a look. And there I show how to extract this data to Excel and then play around with it. So we're almost ready to test this. Just verifying that I have my demo Python program set to port 8082, so I will not interfere with the main Energymeter. And then we also need to update our HTML file with the information for the new values. I have a couple of classes here in the beginning for the 3 different bars that I will show on the screen. Let's uncomment that. We will display the bar as well. Then we have a value that we also want to show, like this. We save that, and then we're ready to start the Python program. And while that's starting up to my Arduino code that I have started in another instance of the Visual Studio Code. And we will see if we can get these to work together. So my Python program is running. My Arduino program is running. And it seems to be uploading okay as well. And if we open up our demo Energymeter site, we can see that we are actually getting values in. As you might know, I want to not to have a lot of values everywhere, so I'm just showing the absolutely minimum. And as you can see here, there's a value here, and that is showing the energy consumption of the heat pump, the total consumption of the heat pump. And since I have that value, I've also added the value for all other energy. So I'm extracting the energy that goes to the heat pump and presenting that here. And even if the colors seem a bit strange on the screen here, you can see the bar that I added down here, or actually down below here. And I will read it for you. So the first part here that is green, it says house, and the middle part says heat, and the third part says water. And this is actually based on the statistics that we created. So this is not at the moment, this is in the current month. The situation is like this. So I can see how much energy I'm spending on water, heating, and the rest of the house. And if we go to the index page and have a look, we will see that we now have a value which is the Energymeter 2. And you can also see that many of them are empty. That's actually because I'm running with the test message still. It will look the same, but it will be populated with all the data naturally when it's using the real Energymeter. And I can show you that from the live system. If we go into the same page on my live system, move down to Energymeter 2, you can see that here I have a lot more values. I have the current, I have the watt hour, what's the effect, we have the energy meter, the voltage, and I'm sure there are a lot more data that could potentially extract from the system as well. But this is really nice, and this is what I need. So I connected the energy meter to the Arduino. So I'm receiving some live data. You can see the frames, they are different size. 4, 5, the last frame is very small actually. You can see that I'm sending 5B, 7B and uploading it to the Medic Mirror. So I've added the message in bytes here as well, so I can see the actual message coming in. And then of course it's clear text and the values as before. So the engine meter is all hooked up, the Arduino is connected and up and running. Thanks for watching and hope you enjoy.